Hello, calculus. We're on 2.6, which is the last section of this chapter, so I hope you're doing okay. This one here is growth and decay. And growth and decay are just exponential models. Growth means it goes up exponentially. Decay means it goes down. Growth we use a lot like in nature and with deer and things like that type of population. And decay is a lot with radioactive material. So let's get going and see how we're doing. All right, when you look at your growth and decay model, it's always this form. This part doesn't change. Maybe it will, right? There we go. All right, so y sub 0 is your initial. It's always exponential, and it's always a continuous growth, so it's e. K is your constant of variation, and t is time. So if k is greater than 1, it is a growth. If it's less than 1, then it's a decay. So let's look here. We have a sugar solution is growing at a rate such that 5 grams grows exponentially to 8 grams after 16 hours. So 5 is where we're starting. So we have done nothing. There's 0 time, and we're starting with 5 grams of sugar. Okay, after 16 hours, so this is my second point, I have 18 grams. I need to figure out what that exponential growth is. So we're solving for K. What we do here is I'm going to end up at 18. Okay, my initial was 5. It's E. I don't know what K is. I don't know how fast it's growing or its rate of growth. It's K. But I do know I was there for 16 hours. So now I just solve. You divide by the 5, and you get 3.6 equals E to the 16K. Now to get rid of E, remember that is a natural log. So now we're going to take the natural log of both sides. All right, so the natural log of 3.6 is 1.28. These two cancel. 16K, so we're going to divide by my 16, and I get K equals 0.08. Okay, you are not done here. This is the K you're going to use in your formula. So now I'm going to use the same formula, but I want to know any time here. So we're going to say the Y is equal to, my initial does not change, E, my time does change, but it's always going to be at a constant rate of variation of 0.08. So 0.08. Are you good? All right, let's continue. Carbon dating. So carbon dating, this is what you use to tell how old something is. So is it truly an antique? How many years old is it? Like, is that really the shroud Jesus wore would be used by carbon dating? Or is that truly the Mona Lisa? You would use carbon dating to see what that was. All right, we know K is equal to this. All right, so, and I want to know the half-life. So what's the half-life of carbon? So to do this, this is a little bit trickier. So make sure you're following along closely. All right, I know I want to have a half-life. So if A is my initial, right, I want half of that is going to give me where I want to go. So we know these A's are going to cancel, just like we did on our other formula. So we're just going to plug in the 1/2 is equal to, my initial was A sub 0, what canceled out, E to the negative natural log of 2 divided by 5600 t. Okay, now we need to look at this carefully because this natural log is telling us something. And this, oh, it's not there. I should go this way. Come on, put my brackets in. There it goes. There it wrote. Okay, so now I can rewrite this a little bit. This natural log of 2 goes here. I can put this negative with this t, and I can rewrite this. So this is e to the natural log of 2 times negative t over 5600. Okay, I know that these two things right here, right? E to the natural log of 2, this is going to cancel. So I know this is 2. So right now I have 1/2 equals 2 times negative t over 5,600. Good with this point? Now, I know this 2 right here is technically 2 to the negative 1. All right, we got that so far. So now I know my bases are the same. So I've got negative 1 equals negative t divided by 5,600. Multiply by the 5,600 and get rid of these negatives, right? So 5,600 equals t. So after 5,600 years, I will have half of my carbon. Kind of cool, right? This part right here, which was the tricky part, is that's 2, and this is a power to a power. Okay, I hope you did well. That 2 should have probably been bigger there. I hope I didn't mess you up by writing that too little. Let's make that a little bigger so we know that that's a power. There we go. I hope you did well. Our understanding. Okay. Compound interest. An effective rate means if I'm compounding semi-annually or quarterly or this, there's a certain rate I could have given you at the beginning of the year that would match that. So the effective rate is what is equivalent to it was compounded annually. So what would my annual interest rate have been? So it's usually like if I was 6% compounded quarterly, it's 6 point something is what we're talking about. So you take 1 plus R over M. R is your rate. M is the number of compounding periods. We use N before. Your book uses M for some reason. I don't know. Minus 1. And the same is true for your continuous. So let's see if we can figure this out. All right, we have 6% compounded quarterly. I want to know the effective rate. So what is my effective rate? So I take 1 plus, you take your interest rate, divided by how many times it was, 2, the quarterly, minus 1. You just type that in your calculator, and your effective rate, you should have gotten is 0.06136. Well, we changed that to percent. 6.14% is your effective rate. Okay, compounded continuously. Now you're using your, you're using your other formula. Come back here, hopefully. Okay, compounded continuously is, so we want the effective rate again. Continuously is your E, so it's E to the 0.06 minus 1. That is equal to 0.06183. So your effective rate is 6.183%. So if you'll notice, it's only 0.04% higher. Okay. Now let's just talk about this. This represents the number of items an employee can produce in a day. Why do you think it does this and has this asymptote? I hope you guessed because there's a limit as to the highest amount you can produce. After a certain time, you will not be able to produce more than that. So this is like a log function, right? How many days before a new employee can produce 20 items? So we go to 20 and we go over. All we're doing is we're reading a graph. This is roughly right here. And it looks like 5. This is an estimate right here, just from graph reading. All right, if you had 6, I'd take that one too. It depends on how good you go. The next thing I want you to do, this next page is just reminding you of your parent graphs. You should know these, all right? If you do not study them and recognize them, because if I give you an x squared, you should know it's a parabola. Absolute value, you should know it's a b. Square root, you should know what all of these look like and their parents. So make sure you have those memorized. All right, that's it. Good luck on your homework, and we'll go on to review next time.